denoted as ES2. The magnitude of the output voltage is then equal to the difference between the two secondary voltages, and it is in phase with the voltage of the left-hand coil. So this is the detailed diagram for the LVDT. So then we have seen V in and V out. That is this ES1 and ES2. V in, that is ES1. E out is the ES2. That is a coil. So this is the diagram we have seen in last class itself. Secondary, it is split into two. One is placed at the top, another part is placed at the bottom. Middle, they are keeping the primary. So the primary will be connected with the input voltage. The secondary will be connected to the voltmeter. This is the simple diagram. Here they have given the detailed diagram here. Same, if these two diagrams are same. This diagram and this diagram both are same. So the next you are seeing means this is the practical diagram. This is the detailed diagram they have given here. So the primary winding AC input we are giving. This is the core. This is called as a core arm. So here alone we are getting the displacement here. Then secondary, already I told you, no, it is split into two. So the one induced EMF is given by ES1, another voltage is given by the ES2. It is connected to the E out. This one. ES1, ES2, E out. It is measured by the voltmeter. Here same. ES1, ES2, E out. It is given here. The score they have given separately. So they everything, the primary and secondary, it is wounded on the score alone, not separate. For the understanding purpose, they are split into the windings and core into the three parts. So the next, then we are getting the we are getting on way that is on practical graph. So it is drawn between the core position and then output voltage. So the core position, we have to change the position with respect to time means. So we'll be getting the output voltage, it will be linear. So if you are changing the direction of the core means, then you will be getting the curve linear, but it will be in the opposite direction. So what happens here is the A position A, you will be getting this point. Then at point B, you will be getting here. There will be the point C also. This is 4 at A, 4 at the null position. The 0 point it is given here. This position is denoted by the null position. This is the 4 at B. So for the different position, for the different core position, you will be getting the linear curve like this. So this will be we are obtaining from the LVDT practically. Practically, we have to change the position of the core. Then we have to note down the output voltages here. So then we have to plot the graph for the LVDT. So this same thing we will be doing in the lab also. So while I'm handling the LVDT, so then I will explain how to change the core position and then how to measure the output voltage for the LVDT, right? So this is the basic for that real-time experiment, right? So you have to clear in this concept, then only you can measure the LVDT output voltages in the lab experiment. So we have to change the core position. The corresponding output voltage should be noted down. Let us see the construction first, then we will see the working in detail. So then first already I have shown the LVDT diagram in the last class itself. This is the detailed diagram for the LVDT. Then next we will discuss about the principle of operation and working. So then after you are doing the experiment, you will be getting the AC output voltage of conventional LVDT versus core displacement. You will be getting like this. The curve will be looking like this. So let us discuss the construction of the LVDT first. So the transformer consists of primary winding. Already I have shown the diagram. So there will be the primary as well as there will be the secondary. The secondary will be split into two coils. One will be placed at the top of the core, another will be placed at the bottom of the core. So the transformer consists of a primary winding, which is denoted by P, and two secondary windings, S1 and S2, wound on a cylindrical former. See, already we have seen. So this is the cylindrical former. This is the cylindrical former, right? So then what happens here is cylindrical former top there will be the secondary winding, then bottom also there will be the part of the secondary winding which is hollow. Cylindrical former which is hollow in nature and will contain core. So the core in the sense it will be made by the some conducting material. Both the secondary windings have equal number of turns. The entire secondary winding which will be split into two, then the number of turns in the two secondary windings will be same. Both the secondary windings have a equal number of turns and are identically placed on the either side of the primary winding. So it is given in the diagram itself, right? So the primary winding is connected to an AC source which produces a flux in the air gap and voltages are induced in the secondary winding. It is same as that of the normal transformer. The next point is a movable soft iron core is placed inside the former and displacement to be measured is connected to the iron core, right? The next one is the iron core is generally of high permeability which helps in reducing harmonics and the high sensitivity of LVDT. The LVDT is placed inside the stainless steel housing because it will produce electrostatic and electromagnetic shielding. So both the secondary windings are connected in such a way that resulted output is the difference of voltages of two windings. See, all of you go through this slide, the working they have given in detail. So I will explain one by one. Go through the slide, then I will explain in detail. All of you go through the slide. Hello? ஓ சொல்லுங்க ம் 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 As the primary is connected to an AC source, so alternating current and voltages are produced in the secondary of the LVDT. As the primary is connected to AC source, so alternating current and voltages are produced in the secondary of the LVDT. The output in the output in secondary S1 is E1 and in the secondary S2 is E2. So the differential output is So the differential output is E out is equal to E1 minus E2. This equation explains the principle of operation of LVDT. Now, three cases arises according to the location of core, which explains the working of LVDT are discussed below us. So the case one is when the core is at a null position for no displacement. When the core is at a null position, then the flux linking with both the secondary windings is equal to the induced EMF is equal in both the windings. This is the condition for the case 1. So for no displacement, the value of output, that is E out, is 0 as E1 and E2 both are equal. So it shows that no displacement took place. This is the conclusion for the case 1. Then case 2, when the core is moved to upward of null position for displacement to the upward of reference point. In this case, the flux linking with the secondary winding S1 is more as compared to flux linking with S2. Due to this, E1 will be more as that of E2. Due to this, output voltage E out is positive. Then this case 3. Case 3, am I audible? My voice is clear or not? Am I audible?
Yes, ma'am.
Okay. Then case 3, when the core is moved to downward or null position, that is called as for displacement to the downward of reference point. In this case, what happens is magnitude of E2 will be more as that of E1. And due to this, output E out will be negative and shows the output to downward of reference point. So this characteristics curve giving the relationship between the output voltage and then core displacement. So it is called as the output versus core displacement curve. A linear curve, this is the linear curve. So linear in the sense when you are increasing the core displacement means there will be the changes, there will be the increment in the output magnitude. So the curve will be linear. So that is the reason it is called as a linear. A linear curve shows that output voltage varies linearly with displacement of core. X-axis we are taking the core displacement. This is what this dotted line. representing the 100 percentage of full range core displacement. This is 50 percentage, this is 0 percentage. This is 180-degree out of phase, this is in phase. This is LVDT's AC output voltage. So this is LVDT null position. AC output of conventional LVDT versus core displacement. This one. And if you go through this slide, I will explain in detail. Some important points about magnitude and sign of voltage induced in LVDT. The amount of change in voltage, either negative or positive, is proportional to the amount of movement of core and indicates amount of linear motion. But nothing the output voltage increasing or decreasing, the direction of motion can be determined. The output voltage of an LVDT is linear function of core displacement. And next we will see the advantages of LVDT. Then first advantage is high range. So the LVDTs have a very high range of measurement of displacement. They can use for measurement of displacements ranging from 1.25 millimeter to 250 millimeter. No frictional losses. As the core moves inside the hollow former, so there is no loss of displacement input as frictional loss, so it makes LVDT as very accurate device. Third point is high input and high sensitivity. The output of LVDT is so high that it does not need any amplification. The transducer possesses a high sensitivity which is typically about 40 volt per millimeter. Then low hysteresis. LVDT shows a low hysteresis and hence repeatability is excellent under all conditions. The next point is low power consumption. The power is about 1 watt, which is very as compared to the other transducers. The last point is direct conversion to electrical signals. They convert the linear displacement to electrical voltage, which are easy to process. Next, disadvantages of LVDT. LVDT is sensitive to stray magnetic fields, so they always require a setup to protect them from stray magnetic fields. They are affected by the variations in temperature. And next, let us discuss about the application of LVDT. They are used in applications where displacements ranging from fraction of millimeter to few centimeter are to be measured. The LVDT, acting as a primary transducer, converts the displacement to electrical signal directly. They can also act as the secondary transducers. Example, the Bourbon tube, which acts as a primary transducer and converts pressure into linear displacement. Then LVDT converts this displacement into electrical signal, which after calibration gives the ideas of the pressure of air. Then electromechanical transducers. So the first example is galvanometer. The second one is accelerometer. So these two are the then example for the electromechanical transducers. The first one is what galvanometer. So the galvanometer is an instrument for detecting and measuring electric current. It is an analog electromechanical transducer that produces a rotary deflection through a limited arc in response to electric current flowing through its coil. Then accelerometer, a device for measuring acceleration and gravity-induced reaction forces. Then next one is rotary motor, linear motor, then vibration power generator are some examples of this type. Next, types of energy transformation. First one, a movement which is converted to voltage. This will be coming under the electromechanical category. Examples, motor or generator. Next example is phonograph, cartridge. This is galvanometer, then this is accelerometer. Go through this slide, I will explain. Next, principle of energy transformation. The first one is electromechanical transducers, some type of mechanical contact. The next point is convert physical change. That is, physical change means movement. It may be movement or distance or etc. to electrical signal or vice versa. So this electromechanical transducers, what it is doing is we convert physical change, movement or distance to electrical signal. So the example for this electromechanical transducers are mouses. That is, mouse. What happens is movement of trackball causes the electric signal. So inside there will be the ball. So this is the ball. This movement of the ball. When you can get this movement of ball is when while you are changing the position of the mouse, means this ball will be moving from one place to another place. That is, you can get the movement of the ball. Movement of track ball. This is called as a track ball. Causes electric signal. Strain gauge pressure transducer. This experiment also, then we will do it in the lab also. So this experiment is there in the lab. This strain gauge is there in the lab also. So we have to perform the experiment with the strain gauge. We have to take the output and we have to draw the graph. LVDT and strain gauge. Yeah. That is the experiment. Both will be coming under one experiment, and that experiment number is, I think, 12 or 10. This content, the details about the LVDT and strain gauge, it is there in the lab manual also. All of you go through the slide. When the tension is applied to the electrical conductor, its length increases while the cross-section area decreases. So its resistance changes. This change can be measured to measure. Used for measurement of force, stress, and strain. A strain gauge is a passive type resistant pressure transducers whose electrical resistance changes when it is stretched or compressed. A pressure transducer contains a diagram which is deformed by the pressure, which can cause a strain gauge to stretch or compress. This deformation of the strain gauge causes the variation in length cross-sectional area due to which its resistance changes. Go through the LVDT diagram I will explain. This is the strain gauge. The wire filament is attached to a structure under strain, and the resistance in the strained wire is required. Go through the diagram. So this one is wire resistance and the strain gauge. Wire resistance and strain gauge. Uh-huh. Okay, we will see in the next class. All of you wait for attendance.